Good afternoon. We'll wait for others to join for a minute, and then after that, we'll proceed. Good afternoon, everyone. I'm gonna go ahead and get started. Let me see. Oops, I was in the process of logging in when you shut up. So here we go. We want the lecture. Boom, boom, this one. Okay. We need to start on a new thing. We had finished solutions, and I told you I would be opening the test soon, so I will do that. But we're starting on gas laws. There are quite a few of them, like I told you. So we're going to look at the first three, the most prominent, I guess we could call. Yeah, that's what these are. Okay, let me download this so we can look at it. All right, here we go. Right, all of gases have certain characteristics to them. And if you remember the kinetic molecular theory, well, there's a part of it that applies to gas. So it's all about pressure, volume, temperature, and the number of moles. So Dalton's law is the first one, and it states that a mixture of gases, the sum of the partial pressures exerted by each gas is the total pressure of the mixture. So if you have a balloon filled with air, right, you have nitrogen, oxygen, carbon dioxide, and other little things, but all of those pressures exerted together would be the pressure that added together, it'd be the pressure that the balloon is exerting. So that's number one. Number two is Boyle's law. And remember, I was telling you about Boyle's law, how you can remember, which one's which earlier. But when you are looking at Boyle's law, if you just remember this one, hold on, let me draw this. And I think I'll do it right. Yeah. So if you just remember the full combined law, so it's P1 V1 over T1 is equal to P2 V2 over T2. Okay, so that is the combined gas law. And in Boyle's, the temperature is what's kept constant. So if you just erase out of the picture the temperature, you see you've got Boyle's law. All right. Because the number of moles and the temperature are constant. There's always two things that you're going to hold constant when you have one of the laws. Okay, the next one is Charles' law. And for Charles, so let's draw this thing again. It's the pressure that's held constant. So if you just erase the pressure, you have Charles' law. You see that? And that's supposed to be over T2, but for some reason it keeps moving on me. But that's how it is. And the next one would be Gay-Lussac or Amonton's law. And that one is the one that's constant. And remember, oh, I forgot about Avogadro's number. Avogadro's number, you have N and V that are directly related, and P and T are the constants. So in this case, when you write it, it would be P1 over N1 is equal, I'm sorry, V1 over N1 is equal to V2 over N2. So just remember it's over and over here. It's just for some reason, it keeps moving on me. I don't know why. When I save it, it just moves again. So let's look at the next one. I forgot about Avogadro's law was in the middle here. All right, the next one is, yes, it sounds like avocado. So Gay-Lussac. So once again, if you take the combined gas law, right, and you just get rid of the volume this time, you have Gay-Lussac's law or Amonton's law. See how that is over it? Yeah, P1 over T1 is equal to P2 over T2. All right, so that's the gas laws in general. All right, let's go ahead and look at more about that. All right, we have, okay, some problems. And the best way to do this is to identify which law based on what's not mentioned, because whatever is not mentioned is being held constant, right? So we're going to read and see what's going on here. And usually what I do is I write things. So this is a given mass of oxygen. So that means N is constant because you notice it's not mentioned again. So N is a constant, but N is constant in all of them. So we know that N is a constant, right? So I'm just going to call it constant because it doesn't fit. Right, the next thing that it's talking about, it says it occupies a volume. So volume of 500, so that's volume 1 of 500 milliliters at a pressure of 760 millimeters of mercury. Okay, so we know that they will probably want, temperature is not mentioned. See, it says at the same temperature. So we know the temperature is constant. So this happens to be Boyle's law. So let's go ahead and write temperature, and both are constant. Okay, both of those are constants. So the next thing to do is keep writing our data that they gave us. It says what pressure, okay, so we need P2, and that's our question. Will it occupy at a volume of 450, okay? So we know that P1 times V1 is equal to P2 times V2. So to solve for P2, that would be equal to P1 V1 over V2, right? And that's going to be equal to, let's multiply 760 times 500. And it's always good to go ahead and write your numbers with V1 and T1, you know, like that, because it helps you know which one's which. Okay, and now we're dividing it by 450. And that gives us 844.44. And they gave us basically three sig figs, well, 2 sig figs. So depends on how picky you want to be, what your answer would be. But that is millimeters of mercury. So if you want to be picky, it would be 840, right? And we're going to be picky, so we're going to be 840 because that is what you would go down to, because it is actually actually it should be just 800, because this one right here only has 1 sig fig. So like I said, it just depends on whether you want to be picky or not. 844, 840, whatever it is, but that's the answer. All right, so we had that. Now let's clear all these drawings and see what we get. All right, next one would be a question. Okay, another one. Let's look at it. Okay, it says 25 Celsius. The volume is this at this much pressure, and then the same temperature. Okay, so once again, it's sealed. So that means that, that the number of moles, so N and T are constants, right? Are constant. So I just put const like that. So we know that. We know that the pressure one, volume one is first, is 5.65 liters. And we know that the pressure one is equal to 14.3 psi. And then we know that the pressure is changed. So we know P2 is going to be 14.7 psi. What is the new volume, right? All right. So since it is in liters, we already have liters. We don't have to convert anything. So once again, we need to solve for, that's a question mark. I don't know why on earth this was 2. I was thinking, I meant to clear that. All right, there we go. That's the question mark. Okay, so V2 is what we're solving for. When you have something that is P1, V1, you know, so you know that is going to be over P2, right? It's going to be our answer. All right, so we have to multiply 5.65. I'm just going to multiply them myself. 5.65, which is the volume, 1, times 14.3, which is the pressure 1. And then you're going to divide it by 14.7. And that's going to give you your answer, which is 5.49 or 5.496. So basically 5.50. And we did have 3 sig figs in this one. And that would be liters. There you go. So you notice that one thing that, have you noticed that as we increase the pressure, the volume decreases. So it is known as what do you call it? Opposite, well, not opposite, but more like inverse, right? Inverse relationship. We have an inverse relationship between pressure and volume. The bigger the volume, the less the pressure. The smaller the volume, the higher the pressure. Okay, so let's clear all of that. Just remember that. At constant temperature, All right, let's go next. And number of moles. All right, let's do another one. Practice number 3. All right, with the sea level thing, you'd have to do what is known as a correction for water. When you do that, this is annoying me. Oh, hold on, I didn't mean to do that. So the correction for water, you have to look it up. And let's see, I gotta look it up. So I will tell you in just a minute what that is. Correction for water. I have to find my little table somewhere in here. I think you probably have it in your textbook in there, easily found, but I'm not looking at the textbook, so I'm just looking at this stuff. So okay. Here we go. All right, so if you have a correction for water, you are going to do a, let's see. I'm not finding the temperature, so we'll skip that one and we'll go on to the next one, and then we'll come back to it, okay? Because this one's with the correction and I can't find it. So let's look at 4. Again, correction for water. Just still over water. Okay, now this one's dry air. Never mind. Sea level, partial pressure of the nitrogen is 601. And the atmospheric pressure. Okay, sorry. I was looking at that. I was looking at the next one and my brain went there instead. Okay, so this is actually partial pressures. All right, you notice they're telling you one of the things, let's underline what we have here. Okay, they're telling you that the atmospheric pressure, right? That's the total pressure, is 760. But the nitrogen pressure is 601. So it says if oxygen is the only other gas, what pressure does it exert? Well, that's easy. You just say the P total, right? So the atmosphere pressure, we just say PATM, so atmosphere, is going to be the pressure exerted by the nitrogen plus the pressure exerted by the oxygen. Well, since we don't know this, right, we need to solve for that. And that's going to be P atmosphere minus the PN2 is equal to PO. The pressure exerted, oh, sorry, that's a funky one. The pressure exerted by the O2. Okay, so in order to do that, you just got to subtract. So it's 760 minus 601. And that is a total of 159. So PO2 is 159. And this is torr, right? Because that's what they gave us our thing in. I told you there are so many ways to measure gas pressure that you have to be aware of what they're asking you. All right, that one was an easy one. This is the next. The next one's the one we cannot do together. All right, the next one is the one that got the sea level thing, and I mean not the sea level, but it's collected over water at a certain temperature. You have to look for that and then do the correction, which we will do that later. We're not going to do that one right now. Okay, so here's another one. Okay, notice that this one is giving us a temperature. One thing that I haven't told you, but you always have to change your temperature to Kelvin because you cannot divide by 0. And sometimes that temperature may be a 0. And so you have to change it to Kelvin always. This is every time. So the very first thing to do is we know that we have 37. And you have this and this. Okay, so that would say this is the temperature 2 or temperature 1. It doesn't matter as long as you're finding 1, right? All right. At the same pressure. So this is the pressure and the number of moles are held constant. So these are the two. So that means this is Charles' law. And Charles' law, remember, is P, it's not P, there's no P. It is V1 over T1 is equal to, okay, so if you put it like this, right, it's equal to V2 over T2. That's our formula. I always find it easier to solve for something that's linear. So when I rewrite this, I write it like this. V1 times T2 is equal to V2 times T1. And that way you can solve for any of them much easier. All right. And we want V2, obviously, right? All right. Okay, so we have V1. V1 over here is 1.5 liters. And that is, and then T1, sorry, is equal to 20. So 20 plus 273 is 293, right? So we have to change it. Remember that to Kelvin. T2 is going to be equal to 37 plus 273. And I just use 273. I don't like the 0.15. And that's equal to 310, which means that V2 is the unknown. Okay, so here we go. We need to substitute over here. So V1 is 1.5. And we're going to multiply it times T2, which is 310. And then we're going to divide it by T1, right? T1 is going to be 293. Okay, my answer is 1.58 liters. 1.59, sorry, 1.59 liters. So V2, the volume at 37 degrees is going to be 1.59 liters. All right, let's clear that. And let's go to the next one. The next one. All right. Let's look at this one. Okay, this is 10 grams of helium are in a pliable balloon with a volume of 2.5 liters at 1 atmosphere and 25 Celsius. Okay, so this is an Avogadro's number. Remember how that one went? N, right? Because Avogadro's number is going to have to do with moles. So we're going to need to change the 10 grams to moles. And then when we get the moles, change it back to grams. All right. So for Avogadro's law, we need the number of moles. And that is, for helium is 4. Hold on, where are you? I'm trying to find my Where are you? Mhm. We have, yeah, we have constant pressure and volume, it looks like. No, constant pressure, sorry, and temperature is what I meant to say. And we have volume that is rested at 1.10 and it started at 2.5. Okay, so in this case, we need to write down the data that we have. I need a piece of paper. Hold on. So we have 10 grams. That's our N, right? That's what we started with. So that's N1. V1 is going to be equal to 2.50. And then we want to know N2, and V2 is equal to 1.1 liter. Okay. N, the nitrogen, the moles of nitrogen. Where is my, I'm trying to find my, my periodic table. Hold on, because it's right here. I just can't get to it. There we go. All right, periodic table. You are telling me that. Yep, it's 4. That's what I thought. So it's going to be 10 grams over 4 grams, and that's going to give you the number of moles. All right, so that's going to be 2.5. Yeah, 2.5 moles of helium. Right, so we know N1 now. N2 we're going to get. All right, so our formula, you recall the formula for this? If not, we can go back. Well, not like that. We won't go back like that. We'll go back like this. So remember, this was our little formula right here. V1 over N1, right, is equal to V2 over N2. Now, like I told you, I like to do these in a linear form. So what I mean by that is I like to rearrange them and start up. Oh, nope, don't go there. Okay, sorry. There we go. All right, so start up by having V1 times N2, right, equals to V2 times N1. So now, since we need to solve for N2, it's going to be V2 times N1 equal over N2 is equal to, no, sorry, over V2 is equal to N2. So let's do that. N2 is going to be equal to V2 N1 times V2 over V1, right? Sorry, I had it backwards. when I said it backwards, but that's what we want. All right, so we have all these numbers. N1 was 2.5, right, moles. And that's multiplied times V2, which happens to be 1.1 liters. That's the volume, divided by V1, which is 2.5, sorry, not 1.5, 2.5 liters. All right, so how much is it going to be left? Let's see, 2.5 times 1.1 divided by 2.5. Well, obviously 1.1. That was easy. 1.1 moles. So 1.1 moles of helium, right? You have to now change it. 1 mole of helium is equal to 4 grams, 4.00, whatever, grams. And that's going to give me times 4. And it's going to be equal to 4.4. That's your answer, 4.4. Do we want a 0? Yeah, 0 grams of helium. That's how much is going to be left. Okay. So you see how all these formulas, like I told you, you can make yourself a cheat sheet. That's what I call them. Not that you're cheating, but because I'm letting you, so it's not a problem. You would be cheating if I didn't tell you to do that. All right. Now look at this one. And so you're working at a fast food joint and you're told to move a CO2 canister to storage. And you change it from its 27 Celsius. So that's temperature 1 is 27 Celsius to the chili cold storage temp of a 10. All right, so T2 is 10 Celsius. If the pressure inside the cylinder was originally, so P1, right, 2.25 atmospheres, what is the new pressure? Okay, so P2. All right, so that's the question. So let's write all of this down because it's in two places, so we may as well have it. T1 equals 27. And remember, we got to change it to Kelvin, so they might as well do that now. 27 plus 273 is going to be equal exactly 300 Kelvin. All right, that's T1. T2 is going to be equal to 10, so that is 283, sorry, Kelvin. Always change it, remember that. And P1 was given to us, and it is in atmospheres, and it's 2.25. Right. And this is a volume, and number of moles are constant. Okay. So this is a Gay-Lussac question. Remember, this one's going to be V1 over T1 is equal to, I'm sorry, B1. I said B1, I meant P1 over T1 is equal to P2 over T2. So on this one, if we put them in a linear form, it's going to be P1 V2 equal to P2 V1, right? V1. Okay. And now we can, did I say V? I did it again, didn't I? I mean to say T and I say V. Ugh, excuse me. It's still correct. It's just T. All right. There we go. So once we do that, we get P1, T2, P2, T1. All right. So substituting that, and we want P2, obviously. So we need to say this is going to be equal to P1, T2 over T1, right? To get P2. All right, so here's our answer. Is going to be 300, no, not 300, 283 times 2.25 divided by 300. That's going to give us 2.12 atmospheres. There you go. That's the new pressure. All right, so that is how you do. Most of these are pretty standard, except for the one I'm going to have to go back to that one because I cannot find the correction over water thing. I don't know where to look for it in the book, or I don't have it in my notes either, or in my, oh, I thought I had it here, but I don't have it here either. So I don't know where it is. I don't know where my correction is. It's not here. Anyway, so we're going to look at gas laws. We have some problems to do, and I'm going to get you guys to do them. I'm going to write just the information down. I'll just read you the the PowerPoint. Hold on, let me say share to a different place because this is not. I don't want to stop share. I just want to do a new share, which is the whiteboard. Okay, so here's the first problem. And you have to recognize who it is. That's the first thing. And you have to recognize the type of problem they're asking you. All right, here's the first one. It says a sample of compressed methane has a volume. So we're going to write that down. Volume, so volume 1, right? Of 648 milliliters. At a pressure of 503 kilopascals. Okay. Question is, to what pressure would the methane have to be compressed in order to get a volume of 216? So volume 2 is 216 milliliters. And the question is the pressure 2, right? All right. That doesn't look like an equal. All right. So first of all, which law is this? Just put it in the chat if you don't want to say it out loud. It's fine. Whoever does it first is fine. Which law would this be applying? Nobody? Okay. Charles is constant pressure. So obviously the pressure is not constant here because it's changing. So who is missing out of the one that I showed you? Which one of the four quantities that we're supposed to know? Boyle's, yes, that's correct. So Boyle's law is P1, right? V1 equals 2P2 V2. So it's already in linear form. All we have to do is solve for P2. P2 is going to be equal to what? Who wants to do that one? I'm helping you with this one a little bit. Okay. Come on, people. Let's work on it. You got most of the information right there in front of you. You have 3 sig figs in all of them, so. Nobody? Okay. That is the right answer, but we have 3 sig figs, so what would the better answer be? Okay. Oh, because now you're decreasing the pressure. You have to make sure that you have the same place, right? Which was 1,509. It's going to be 1,510. And there's your answer. All right, pretty good. All right, let's do another one. Okay. This one says this. A weather balloon contains 5.30 kiloliters of helium. When the temperature, so this is the volume, right? When the temperature is, that's V1 and this is T1, is 12 Celsius. Then it says, at what temperature will the balloon's volume be 6.00 kiloliters? That's a period I'm trying to put there, but it won't come on. All right, so the question is the temperature, right? All right, so first of all, law. Yes, this is Charles' law because the pressure is constant and so is the number of moles. Therefore, the formula would be normally, right? V1 over T1 equals V2 over T2. Like I said, I like to make this linear so it's easier to solve. So it's really V1, T1, T2 equal to V2, T1, right? All right, so we're solving for T2. What's our answer? And that's going to be in Kelvin. Your answer is going to be in Kelvin. Don't forget, you have to change it. And watch your sig figs too. Yeah. Yeah. You really have to watch your sig figs. Just on the answer. Not when you convert it. You really don't. Because the conversion is different. Okay, so what do we get? This is a little more complicated because you got to do more. See, this you have to convert to Kelvin. So you got to use 285, right? And when you get your answer, it's going to be in Kelvin. So then you got to convert it to Celsius. Yeah. Nobody? You don't have it yet? All right. Okay. So when you solve for T2, right, you're going to get V1 on the bottom, right? So V1 is 6 kiloliters, 6 point. This period doesn't want to appear here. In the top, it's just going to be the two that are up there. So 5.3 kiloliters, not 530, but 5.3 times your Kelvin, right? Don't forget you have to change it to Kelvin. Since you changed it to Kelvin, you're going to get an answer in Kelvin. And they want it not in Kelvin. So it's 5.3 times 285. And then you divide it by 6.00. And that gives me 252. That's what I got. No, that doesn't look right. What did I do? What did I do? Oh, I multiplied the wrong one. Let's see. Yep, I did. I put the T1 in the wrong place. Yeah, no. I did. I inversed them. That's what I did. I did inverse them. I was like, wait, that should be 6 on top and 5.3 on the bottom. This is why it's good to write them down, you see, because otherwise you can get confused. And I just did, but I noticed because there's something wrong here. Okay, so V1, right? We said V2. See, that would be V2 that goes up in there. So it's 6.00 on the top divided by 5.30. Okay, so now it's correct. I got 322.6. So sig figs tells me this is 323 Kelvin. Subtracting 273 from that so that we can get the Celsius back, right? It gives me 50 Celsius. See? So that's how you do it. Okay. Just, well, actually 49.6, which is good enough for 50. All right, let's go to the next one. One more. We have another one. You got to learn to recognize these. All right, we have, well, we have not done that one yet, but yeah, Okay. Oh. No, we don't want Avogadro's yet either. This is not Avogadro's law. This is a different law. This is the principle. Yeah, no. No, you can't do that one either. Okay, so I have another thing that we use. Let me go there and show you the one that I'm talking about. I'm gonna reshare back to here. And hopefully it's on here. Let me go see if this one's here. Hopefully it is, this file that I like to use. It kind of helps you. If it's not, I'll post it later. Hold on, where are you? Okay, yeah, this one. I like this one because it's a magic square. So basically you have a lot of problems and they're all the kind of thing that you can do. So let's go ahead and try to solve the magic square. Someday. There we go. All right, what is a magic square? Well, it has a number that you have to find. But first you have to change it, right? All right, so the first one's a gas conversion. Remember, I told you would have to do those. The next one's an actual problem. The next one's another problem. This one is a Celsius problem, but it is also a problem. So in other words, you have to convert it back. This one's just another problem. Yep. Okay, this is another conversion. So the A and F are conversions for gas. The starting volume. Okay, that's another problem. That's another problem. Yeah, there's only two that are gas conversion problems. The rest are all problems. You just got to identify which kind so you know which ones. And the answers are here. Obviously, based on the answer that you get, you put that number on there. And that's your magic square. So let's say, I'm not saying that this is the right answer. Let's say that one, that the first one, A, was, I don't know, let's pick one. Let's pick 9, just to say 9. Okay, so you would put, excuse me, instead of the answer, you would put the number of the answer up there. For example, 9 in this case, if it were 9, I'm not saying it is 9. Shiloh, give me a minute. That's my kitty. And then whatever other answer, you put that answer number there and the other answer number there. And the magic square is that all of the squares, whether you're going horizontally, vertically, or diagonally, have to add up to the same number. Now, and like I said, that doesn't mean this is right either. I was just giving an example. So let's see if you guys can solve this magic square. Hello, give me a minute. Oh no, sorry, that first one is not a conversion question either. It's another problem. Sorry. I had a cough attack there for a minute and my throat got dry. Sorry. Excuse me. Okay, that's the answer on that one. Mm. You have to be able to look at that bottom thing too. So I don't know if you guys can download it and look at it, but okay. B. Okay. Mhm. So that was 2. Mm, oops, sorry. 7. Okay. D. You guys getting anywhere? These are cool problems. You like the way this works once you do it. Okay. Let's see. Okay. Okay, let me see if that's in there too. Yep, okay. Yep. E to what pressure? So P, that's P2. We do not know. The volume is 48.0 liters. P1 is 99.3 kilopascals. All right. In the second volume, it's going to be 16. Okay. Okay, so this is P1 times 99. Yep, that's okay. Good. We're doing good. How's your problems coming along? How many have you done? Any at all? You might want to take a picture of the bottom area so that you can fill in your magic square. So once you've solved a few, you'll know the answers. All right. You go ahead and complete it over the weekend, and we'll look at it next time, and we'll go on to ideal and combined gas laws. I've already got enough of them done to know the answers to the rest, but in your case, you'll find out. All righty, you all have a wonderful weekend, and I will talk to you, see you actually in person Tuesday. Bye. You didn't. You're good, Christopher. I had already gotten you. You too, Diamond.